the conference. It is my pleasure to introduce the first speaker, who is Kauffman. Are you ready? Lou, can you hear me?
Yeah, I hear you.
Oh, great. So let us start.
Pardon me?
So let us start the conference. Let us start with your talk. So we are here in Sochi, in the Black Sea, and you are in Chicago. So are you ready to start?
Yeah, I'm ready.
Beautiful. So please start. Now,
Shall I start?
Professor Kauffman from Chicago, please.
Shall I start?
Yes, please.
All right, fine. So this talk is about knotted vortices and reconnection. And it also will, at the end, we will talk about how these ideas will apply to virtual knots and links. What you're looking at in this picture here is a knotted vortex in water, which was produced in the lab by William Irvine and his graduate student Kleckner back in 2012. And we'll get to that. The background here is, of course, Lord Kelvin's theory of vortex atoms, which got people interested in the idea of vortices in liquids. And Kelvin's idea was that atoms were knotted vortices in the luminiferous ether. Eventually, that theory had to disappear because the concept of the ether changed quite considerably. But in the meantime, Kelvin genuinely and seriously was considering various kinds of knots and links as models for possibly for atoms. And this led to the beginnings of knot theory in the construction of the tables by Tate and Little and Kirkman. And Maxwell was involved as well in thinking about knots. So this goes into the early history of the knot theory. And even other people who were interested in philosophical ideas, such as the mystics Besant and Ledbetter, got interested in the idea of knots in the ether. These ideas continued on into the 20th century. For example, here is a paper by Herbert Yela, a rather good physicist in the 20th century, who had the idea that the same idea as Kelvin, really, but in a quantum mechanical mode, that elementary particles should be knotted flux lines, quantized knotted flux. And he wrote some papers about that, but it didn't take off. But of course, this is a precursor to string theory, which also doesn't have much knotting in it in a direct way. But it wasn't actually until 2012 when Kleckner and Irvine did their work and published this paper that people actually produced knots in fluids that you could actually see, knotted vortices in fluids. And they did it by a constructive process. You can produce a vortex, not knotted, by creating a template like the one I'm showing you here on this slide, which is obtained by rotating this teardrop form around in a circle. And the teardrop, if it were in 2 dimensions and pulled downward through a 2-dimensional fluid, will create vortexing at the very tip edge of the teardrop. That will happen. And if it's rotated around in 3 dimensions, then it will create a ring vortex where the fluid will be going around the ring like that. And the idea of Kleckner and Irvine was quite simple. Let's make a knotted template. And they had the opportunity to do that by using 3D printing and tinkering. And so they made knotted templates like the one you see at the bottom of this slide. And they had other good equipment so they could pull that template quickly down through fluid and and then see the vortex. And then in order to see the vortex, you needed to use high-speed photography because it tends to decay very rapidly. It's the decay of the vortices that we're going to be interested in here. But here is the production of an unknotted vortex by that method that I was telling you. Pull it down quickly and the vortex occurs. And this is the residue of the high-speed photography that you're seeing that is showing you this nice unknotted vortex. Now you do the same thing with the knotted temp. Oh, there's a picture of it, still shot of it. Now we're going to pull a knotted vortex, pull, and you see there is the knotted, we're pulling a knotted template and we get a knotted vortex. I'll do it one more time so you see it. And so you get pictures and direct evidence of knotted vortices and fluids in this way. And these are very short-lived. I don't know the time parameters, but they're very short-lived and they tend to break up. And one of the main ways in which these vortices break up is like this, by a reconnection. Two vortex lines come near one another and go into an interaction, and out of the interaction comes a reconnection of the vortex. So from the point of view of knot theory, that's a re-smoothing. That's what we call a re-smoothing, where you cut out two lines that are going parallel and put in two parallel lines in the other way. So they undergo a re-smoothing, and they tend to undergo a number of these re-smoothings and turn into unlinked and unknotted littler vortices, independent little vortices. So, so a while back, well, they of course wrote a number of papers with a lot of people. A while back, we wrote a paper together about untying vortices, and we're using in our modeling a well-known method of producing vortices in a computer space, which corresponds to superfluidity, using a nonlinear Schrodinger equation evolution. And in those vortices, there is a phase. You see that you can think of this as being a wave function. So it's a radius times a phase. And if you have a singularity in the phase so that the phase is not well defined, then that can be a one-dimensional singularity in the phase, and that's the vortex. So the circulation is a phase circulation around the vortex. And you can do computer experiments with these things like this one. And there you see the reconnection happening, in this case simultaneously at all three crossings. So you started with a trefoil knot and it came near itself and underwent the reconnection like that. So what's the geometry of this for doing knot theory modeling? Very simple. The vortex is going around the curve. So we can orient the curve in relation to the vorticity, in relation to the direction of the vortex, by the right-hand rule. So I use the right-hand rule and get an orientation for the vortex current line itself. And then you see what the reconnection scenario is, that when the fluid in between the two parallel lines is running in the same direction, that means the lines are oppositely oriented. And that's when it can turn into essentially one fluid running through in between, and then some interaction can occur and it can change from one of these to the other. Now, the details of that and modeling that and how to think about the geometry of that, of course, is not something we're going to try to do here. We're just going to say it happens. And then in knot diagrams, you would say, okay, if I have an orientated line and another oriented line, and I let myself do a reconnection like that, well, that's recognizable. That's going through an oriented saddle point from the point of view of the knot theory. That is, in time, that's going through an oriented saddle point. I will draw a picture in a moment, but that means that from the point of view of the knot theory, we can diagram topologically the world line of the evolution of these vortices as they go through their reconnections. And also we can just draw pictures of what happens. So for example, here's a trefoil, and by doing a reconnection right there at one of the crossings, you see I end up with a Huffling. And then by doing another reconnection, I end up with an unknot. So it appears that I needed to do 2 reconnections in order to get to an unknot. And that, in fact, is correct. That's the least number of reconnections that you can do to a trefoil knot, no matter how you did it. And there's the topological problem. You're allowed to do oriented reconnections of that kind. And what's the least number that will take you to the unknot or the unlink? That's the question. Another experiment in the computer world. Here's the knot 6-2, and here's a picture of it evolving in the nonlinear Schrodinger equation method. And as you see, it started in 6-2, and it went through a reconnection and became a link, L here. Then it became the trefoil knot, and then 2 more, and it got unknotted. So you might wonder, well, is that the best you can do for 6-2? It's a way in which 6-2 can cascade down to the unknot. Is it the simplest way, or can we do it more quickly? Well, let's take a look and find out. This is just a picture in more detail of what the previous slide was showing you. 6-2 turning into a link, turning into a trefoil knot. Now, as I said, the point of view here in physical language is to consider the world line of the vortex as it goes through its singularities, or from the point of view of knot theory, it's to consider cobordisms of these knots, of which the cobordisms that we're looking at, particularly that are happening physically, are just being generated by going through saddle points, like I've illustrated here. But the more general cobordism, of course, allows births and deaths of circles, and we have a theory about that ever since Fox and Milner, thinking about cobordisms of knots. And we have the question, which is sometimes answerable: what is the least genus surface in the 4-ball that bounds a knot in the 3-sphere, and such like questions. So in the case of the trefoil and its 2 reconnections to get to the unknot, you see that 2 reconnections corresponds to doing 1 bit of genus in the surface. So if you have a knot which requires genus G, then in order to bound in the 4-ball, then it will require at least twice that many reconnections, because every single genus involves at least 2 reconnections. So we have a lower bound of the 4-ball genus on the reconnection number. Now, 6-2 got reconnected this way when we were looking. I'm doing some examples. 6-2 got reconnected this way when we were looking at it, yes. But here's a trick. You can switch a crossing and create a cobordism between the knot before and after switching, and you add 1 genus when you do that, 1 bit of hole, one little genus on the surface, and 2 reconnections. And you can see it as 2 reconnections in the following way. It's interesting to see it because, well, it's interesting. Let's talk about it. So I assume that I have a little curl nearby my crossing. I could push one in. And then I go through the saddle point. And then I have a little line which is going under, and I pull it out and I push it back over, and I go through saddle point again. And now I have switched the crossing. All right. So the only thing about that is that you could wonder, well, in what physical situation might something slide under or over something else in order to facilitate such a thing? in the sort of evolutions we were looking at in the Schrodinger equation evolution, it didn't look like that kind of thing was very likely. I think we have to go back and do more experiments to see if that kind of thing ever occurs. But it seemed unlikely, and that meant that while it was the case that that 6-2 could be done in only 2 reconnections, that is by 1 crossing switch, it didn't happen that way. You see, it is true that 6-2 can be done in only 2 reconnections, not 4, because if you switch that middle crossing, it's unknotted. So that could be done in 2 reconnections. You can imagine that the physical scenario looked something like this. Saddle point reconnection here, pull that little guy under and then back over, and then do another saddle point reconnection, and it's unknotted. It could be that way, but this is not a physical picture. This is just my drawing of a possibility. So we've seen that a physical sequence of reconnections takes 6-2 to the unknot in 4 steps. In principle, it can be done in 2. So what about some bounds? Well, one bound that we can use, and I'm going to go quickly because there are a number of things I wanted to say this time. So I'm just going to state the theorem. The signature of the knot in absolute value is less than or equal to the reconnection number. And the reason for that is that twice the 4-ball genus is less than or equal to the reconnection number. And the signature by Murasugi's theorem is less than or equal to twice the 4-ball genus. So therefore, the signature in absolute value is less than or equal to the reconnection number. Signature of the trefoil is 2, so that's a proof that the trefoil really needs 2. And the signature of 6-2 is also in absolute value 2. So that proves that 6-2 needs 2. And therefore, its reconnection number is 2. R of k is the reconnection number. It's the least number of oriented saddle transitions needed to undo the knot. We'll skip the definition of the signature, but I do not want to skip the Seifert surface. Here is the classic Seifert surface. You smooth every crossing in an oriented way, add disks to each of the circles, and add little twists back at each of the crossings, and you get an oriented surface whose boundary is the knot. The genus of that oriented surface is worth knowing, and it is this. Excuse me. Let me go to that first. The genus of the Seifert surface is equal to 1/2 the number of crossings in the knot minus the number of Seifert circles plus 1. You can prove it by using Euler's formula and looking at Seifert's construction. For example, in the case of this trefoil knot, the number of Seifert circles is 2, the number of crossings is 3, and so crossings 3 minus 2 Seifert circles gets you 1, and 1 is 2. Divide by 2 and you get 1. The genus is 1. This is, in fact, a punctured torus. So it's worth remembering that twice the genus of the Seifert surface is equal to the number of crossings minus the number of Seifert circles plus 1. Now let's go back. There's another way to get to the Seifert surface that's related to reconnection. Suppose I do a reconnection at every crossing. Oh, but then I get exactly up to topological type, I get the Seifert circles again. I get exactly that. You can think of doing the reconnection as smoothing the crossing with a little curl at it. And so that means that one way to undo a knot is to do a reconnection at every single crossing. But also, it's related to the Seifert surface, as you see. So we have some results related to the signature, which we can generalize for links. But I want to talk about the next result, which I think is stated on the next slide just as well. So this is the result I want to talk about now. If I have a positive link, and that means that every crossing type is positive, a given crossing is either positive or negative, and you take it to be positive if I take it to be positive, like the trefoil knots crossings are all positive. So if you put your fingers in the direction of the overcrossing line, your thumb points in the direction of the undercrossing line, those are positive crossings, and the trefoil is a positive knot. So there's the large class of positive links and knots. And then we have the following thing that we can immediately say, knowing Rasmussen's result. Rasmussen proved that a positive link or knot has four-ball genus equal to the genus of the Seifert surface. Now, I'm going to give you a sketch of how Rasmussen proves that by using Corvanophomology, because I'm going to talk about generalizing these results to virtual knots. But for the moment, just accept it. We know that the reconnection number is greater than or equal to twice the four-ball genus, because every bit of genus requires two reconnections. Therefore, the reconnection number of a positive link is greater than or equal to C of k minus S of k plus 1. It's equal to the greater than or equal to the number of crossings minus the number of Seifert circles plus 1. And now with that and an elementary construction that I will show you immediately before going to Corvanophomology, we get that it's equal. So the reconnection numbers for positive links are in fact exactly the number of crossings minus the number of Seifert circles plus 1. And all we have to do to prove this, relying on Rasmussen, is to show that we can do it in that many steps. And here's how you can do it in that many steps. Form the Seifert circles. Now, if you look at the Seifert circles, you see that you could chain them back together with one less than the number of Seifert circles reconnections there. I want to leave these circles connected to one another at the places where I have the dotted lines. And I'm going to do it in a chain so that there are no loops of circles in there. Do it that way in a tree-like form. And that means I will not do reconnections at those crossings. So I'm going to do reconnections at all of the crossings except the ones that have been checkmarked on the original upper left diagram. And that leaves me with an unknotted knot because of the chaining. And this will work for any knot, not just a positive knot. Any knot can be undone by the number of crossings minus the quantity, one less than the number of Seifert circles. And of course, that's the number of crossings minus Seifert circles plus 1. Any knot can be undone by that many reconnections. So that means that with the positive knots, those come together because that's the lower bound. And so you can achieve the lower bound and you're done. And so we have proved here, for example, that this positive knot that you're looking at has reconnection number 6. So that's the proof of this theorem relying on Rasmussen. And so it's nice to know that we know the reconnection numbers for lots and lots of examples. Here's a couple more examples. This link has 4 crossings, 3 Seifert circles, so the reconnection number is 2. And indeed, you can do it in 2, as I've indicated over here. But if you started with the wrong reconnection to begin with, it could be larger. Like in this case, on the lower left of the slide, I did a natural enough reconnection, but I get 2 hop links, and then each of them requires another reconnection, so I'll have to use 3 if I started that way. So some cascades will be most efficient and some will be less efficient. Taurus knots is another good example. If you look at a Taurus knot and do the counting, and I've only indicated it on the slide and I won't walk you through the counting, but if you do the counting, number of crossings is Q minus 1 times P, one less on one of the Q or the P's, and the number of Seifert circles is Q. And you add up this quantity, C of K minus S of K plus 1, and you find it's P minus 1 times Q minus 1. That's a well-known calculation and shows you that the Seifert genus of the torus knot is P minus 1 times Q minus 1 over 2. And so Rasmussen tells us that that's its four-ball genus. And that, by the way, is Rasmussen's proof of the Milnor conjecture that torus knots have that genus, which was previously proved before Rasmussen by Kronheimer and Borovka using more analytical methods. This is Rasmussen's proof is by pure combinatorial topology. So that's how this is related to reconnection numbers. So we know the reconnection numbers of arbitrary torus knots of type PQ. They are P minus 1 times Q minus 1. And if you had a slice knot like this one here, you might not produce any genus, but you can still see what the reconnection numbers are. And you can play around with the different ways in which things are separated. So that's the story about the reconnection numbers of a nice infinite class of knots and how that's related to thinking about vortices. Let's talk, oh yes, and people are interested in the cascades of reconnections. If you're going to do a cascade of possible reconnections and you know the reconnection number, then you can look for those cascades which are most efficient and other questions. So knowing these numbers means that we can redo some of these cascades and get some information about what's ideal and find out what actually happens in certain processes. So there's experimenting to be done, as well as more mathematics to be done. Now I want to talk about the Corvanophomology. So this is going to be a quick review of Corvanophomology and the Rasmussen invariant. And then I'm going to talk about how Corvanophomology gets generalized to virtual knots. And then we're going to see that everything I've just told you works for virtual knots as well, so that I will get you a sketch that the reconnection number of a positive virtual knot is also given by that same formula, number of crossings minus number of Seifert circles plus 1. But I have to tell you what a Seifert circle is for a virtual knot, of course. So let's pretend that you never saw Corvanophomology so that I can make my sketch, okay? So Corvanoph had a very beautiful idea related to the states of the bracket expansion for the Jones polynomial. His idea is that there's an ordering on the states. If you think of states being, well, let's go over to bracket for a moment. In the bracket expansion, there's two ways to smooth the crossing. One I call A and the other I call B, or A inverse. And the A smoothing is obtained by sweeping the A smoothing is obtained by what you see here, and that can be defined in terms of the crossing, independent of the fact that it looks horizontal in this picture. I won't bother you with the definition of the A smoothing. But you can start with the A smoothed state, and then you can do re-smoothings. And if you do a single re-smoothing, you run an arrow. And every time you do a single re-smoothing, you draw an arrow from that state to the recipient state. So first we go to states on the first tier that have 1 B, and then we go to states that have 2 B's, and then we go to states that have 3 B's. And if you look at the resulting arrow structure, it has the form of a cube. And it also is a category, of course, in the sense that the pictures of the states are the objects in the category, and these arrows generate the category. The category is a functorial image of the cube category, which is just the abstract cube with A's and B's festooning its objects. A much simpler category for which any given knot with n crossings, any given knot with 3 crossings, of which there's only 1 or 2, of course, the not in its mirror image. But anyway, if you have an n crossing knot, you have an n cube, and you get a functor from this abstract cube category to a Corvanoph category associated with the knot, like this. Now, Corvanoph is asking then, how can I use this category to get more information about the knot? I want to get more information than is in the bracket polynomial or the Jones polynomial. So that means that you want to think about how does the category as a whole change when you do a Rademeister move? And what kind of techniques can you use here? Well, if you're up in the idea of a category, then you can use the idea of homology of categories. And in the case of the cube category, so I'm making a long story short here. In the case of the cube category, there's a natural homology related to this category, which is simpler than the most general way of doing homology for categories. The idea that fits here is to take a grading, which consists of 0th grading is the A state, 1 grading are the states with 1B, 2 grading is the states with 2B, and 3 grading is the states with 3B. Take the associate, prolong your functor so that each of these objects becomes a module so you can do homology. Take the direct sum of all the horizontal things. So you take the direct sum of all the ones with single B. You take the direct sum of all the ones with 2 B's and all the ones with 3 B's and so on. And take an alternating sum of the arrows that go from the 0 thing to the 1 thing, from the 1 thing to the 2 thing, and from the 2 thing to the 3 thing. And you get a chain complex if you're lucky. So that's what he did. And figured out how to make a chain complex that would work here and take its homology. And that's the Corvanophomology. Now, a little more detail. Oh, I wanted to say that I like to think about the very elementary things that are associated with this. And one of them is indeed the cube category. You see, the cube category is kind of a retrograde motion if you think of the history of the mathematics. Back in the 16 and 1500s, Cardano and Tartaglia figured out how to solve the cubic equation and other things without using our nice, convenient algebra, by thinking about the decomposition of a plus b cubed in terms of the way a cube is decomposed. And they thought geometrically about it. Here, we put an arrow in place of the plus sign and come back to the structure of the cube all over again as a category. So it's interesting to realize that we're back to algebraizing the cube in yet a different way than Cardano and Tartaglia. You know the bracket. So you should think of these re-smoothings that we're going to do, these arrows that go from an A to a B or an A to an A inverse, as saddle point transitions as well. That's very interesting, but these are unoriented saddle point transitions, and so they do not directly apply to our reconnection problem. Nevertheless, that's in the background of the possibility of using this technology to get at problems about reconnection. And when we have an arrow from a single circle with a state on it, it could split that circle in two. And when we have an arrow between for a re-smoothing that joins two circles, that can happen as well. From the point of view of algebra, this is going to be a coproduct on the modules, and this is going to be a product on the modules. And then Corvanoff defines a module associated to each state to be the tensor product of little modules associated to each circle. And the little module associated to a given circle is the module generated by 1 and x with x squared equal to 0. So it's just thinks of the form a plus b x, a times 1 plus b times x. And the generators are 1 and x. And you can visualize the generators of the module by thinking of a circle that's labeled with a 1 or a circle that's labeled with an x. And then the coproduct turns out to be x tensor x for x, and 1 tensor x plus x tensor 1 for 1. And the boundary map then adds up all of these module maps that happen individually back up in here. So when we're back up here looking at this, you're going to have the tensor product of 2 of those elementary modules starting at the top, and they're all going by multiplication into single modules, and then you're taking the direct sum of those and the alternating sum in an appropriate way of the maps that go out. And similarly, at the next level, you get some coproducts and so on. And those are the boundary maps, and one can verify that boundary composed with boundary is 0, and you have homology going. How is this related to the original bracket polynomial? It's important. If you go back to the bracket, then you can match in the way it's related by rewriting the coefficients of the bracket with a 1 times the A smoothing and a minus Q times the B smoothing, and take the value of the loop to be Q plus Q inverse. This is just a rewriting of the bracket with changing variables, and you can normalize it to get the Jones polynomial by counting positive and negative crossings and using a coefficient like that. So it's the bracket again. And now you see the value of a loop is Q plus Q inverse. And so we can think of that as the value of a labeled loop, one labeled plus and the other labeled minus. And these labels correspond to the module labels that we just talked about by taking plus corresponding to 1 and minus corresponding to x. And so then you have that the evaluation of the loop is given by the evaluation of the loop labeled with the module generators, and you add them up. But getting back to the bracket, with this version of labeling them, you can then write the bracket as a sum over all of these labeled states, labeled with pluses and minuses. And it's correctly a sum of monomials now. And the monomials are easy to understand what you read off. You get a minus sign only when you have a B smoothing. So you get minus 1 to I of S, where I is the number of B smoothings. You get Q to the J of S, where J of S is, well, you can get a Q from a B smoothing, and you can get a Q from a plus circle, and you can get a Q inverse from a minus circle. So J is equal to the number of B smoothings plus the number of plus circles minus the number of minus circles. And so the bracket is the sum of monomials. And then you can go another step and realize that what we have called the ith tier in our situation, I being the number of B smoothings, well, that has a number of generators, and it has generators with various J values. So the ith level becomes a sum over sub pieces which have a given value of J. And we can rewrite the bracket as a sum over arbitrary I and J minus 1 to the I, Q to the J, times the number of states that have I, B smoothings and have the value J. And that's the dimension of this module, Cij. Now you can take that. This is repeating that. You can take that sum that I just showed you and rewrite it by summing over J and then summing over I. And you're looking at an Euler characteristic there. The sum on I minus 1 to the I dimension Cij. And that would be an Euler characteristic if the boundary map had the wonderful property that it preserved J. And Corvanoff's map does have the property that it preserves J, so that there are a lot of chain complexes here, one for each value of J. Remember, J is the contribution of Q. And so it's equal to the number of B smoothings, yes, but also it adds in the count of plus the number of pluses minus the number of minuses. So you're looking at the Euler characteristic of the Jth complex, and the boundary is giving you a homology for the Jth complex And so we get this, that the bracket is equal to the sum on J of Q to the J, Euler characteristic of the Jth homology. Or the homology is graded like that. And this is called the graded Euler characteristic, of course. And we have the result here that the bracket polynomial, as we reformulated it, is a graded Euler characteristic of the Corvanophomology. The grading is important. That's why I've mentioned it. And that is the sketch of how you define Corvanophomology. Now, the remarkable thing is that there's more than one way to do these homology theories by constructing a module. And in fact, this is a generalization of Kovanov's algebra. If I had let k equal to 0 in the formulas you see on this slide, the epsilons have to do with a co-unit, and I won't bother you with it. If you let k be equal to 0, you would have x squared equals 0, and it would be Kovanov's. But you can also have k equal to whatever you like, an arbitrary thing. If k is equal to 0, the coproduct on x is x tensor x. The coproduct changes as a function of k. It still works. You can verify that you still get a homology theory. It's still going to be invariant under the Rademacher moves up to grading shifts and everything. When k is equal to 0, it's Corvanophomology. When k equals 1, it's called Lie homology after Yun-Soo Lee, who discovered it. And you see, the Lie homology, it turns out, is actually easier to analyze. And one can make a comparison between the Lie homology and the Corvanophomology, and that's what gives rise to the Rasmussen invariant. So here's Lie's algebra, and the thing about Lie's algebra is that it doesn't preserve the J anymore, so it isn't directly related to the Jones polynomial. But you do have that the J of the boundary of an element in Lie homology is greater than or equal to the J of the element. So there's a filtration by J that you can look at. And by using this filtration, let me skip to that description. By using this filtration, you can create a spectral sequence, and you can interrelate the Lie homology and the Corvanophomology. And Rasmussen notes that by looking at the gradings and using the spectral sequence, you can define an invariant from the Lie homology elements that will be invariant under cobordism and have nice properties. And the properties that it has are like this. Rasmussen's invariant is an integer, it's additive under connected sum, does nice things on mirror images. And when you take a positive knot diagram, it has the property that I was telling you about. And it behaves that way on Taurus knots, and it's less than or equal to the four-ball genus. So very nice invariant. And now let's go back to the Lie homology. The Lie homology can be rewritten by writing 1 plus x over 2 and 1 minus x over 2. And then you find that you get generators R and G, which have the property that their product is just 0. And the coproducts are tensor products of R with some signs and a factor. And the result of that is, in classical knots, that if you take we're back to Seifert, if you take the Seifert smoothing of an oriented version of your link, you can alternately color it with red and green, and then you get an element in homology. And if the state you're looking at has no self loop, if the state you're looking at has only multiplications, then it'll be a cycle. And indeed, in classical knot theory, the state you're looking at only has multiplications, and you have a cycle. Furthermore, if the link is positive, these are all A smoothings. And that means that you're at the top of the complex, and it can't be a boundary of anything because there's nothing coming in. So you're looking at a non-trivial element in homology. And that non-trivial element in homology is the one that you use to test for the Rasmussen invariant. And in fact, things like that generate the homology. So, so that's how the Rasmussen invariant ends up working so well for positive knots and links, because of these elements, non-trivial elements in Corvanophomology up at the top of the complex, coming from Seifert smoothings of the link. Okay, so now I want to talk about quickly virtual knots and links. And so you may recall that virtual knots and links can be defined diagrammatically by adding a new crossing, which is neither over nor under, which satisfies rules which say that it really is just connecting points to one another, and otherwise it's not over or under, it's just a connector. And so one adds these extra rules that say you can do what you like as far as Reidemeister moves is concerned with the virtual crossing by itself, and it can be detoured back and forth across a standard crossing. The interpretation is in terms of knots in thickened surfaces. If you take your virtual knot, you can think of it as a projection from a knot which is living on the as a diagram on a surface or as an embedding in a thickened surface. And in fact, virtual knots taken up to the diagrammatic equivalents that I showed you a moment ago are equivalent to knots in thickened surfaces up to handle stabilization. You can imagine adding an extra genus to that surface that didn't interfere with the knot at all, and this projection operation wouldn't see it. So because the projection operation or the neighborhood, taking a neighborhood of the knot operation like I've illustrated on the right, don't see extra genus, this theory looks at knots in surfaces up to stabilization by one handle addition and subtraction, and that's virtual knot theory. So that means that if we were thinking of reconnecting vortices, we'd have to think about how vortices might act inside a three manifold. What would vortices be like if they were happening in a thickened torus or a thickened double torus? Or more generally, what would vortices be like if they were happening in a three manifold? So that's a nice question, and maybe the physics can tell us something about vortices in three manifolds. Now, spanning surfaces for knots. Seifert circles still exist, and so does our reconnection sequence. I do not always have a Seifert surface that I can build in the usual sense for a virtual knot, but I can go through reconnection at every crossing and get a cobordism to an unknotted collection of circles and cap them off with disks and get a surface that bounds the virtual knot in what I'll call the virtual four-ball, a formal surface that bounds the knot. But nevertheless, a surface, you can ask, what is the least genus surface that you can build in the virtual four-ball in this sense? And all of that. And the genus of this surface is equal to 1/2 of the number of crossings minus the number of Seifert circles plus 1, if you bound it off with disks. That's exactly the same properties as the Seifert surface, but it's a virtual four-ball genus surface. And we can do virtual knot cobordism by allowing saddles and births and deaths. And look at the corresponding cobordism surfaces. We can talk about concordance if the cobordism surface is genus 0. We can look at cobordisms where we can look at slice knots. So for example, this virtual stevedores knot is slice, and I'll just slow down for a moment and go through it with you. I'm going to go through one saddle point, one reconnection right there. And then you see this virtual diagram over on the top right, and you see a long detour of 3 virtual crossings going along from the lower right to the upper part, and that can be just picked up and put elsewhere by the virtual moves, and then you see it's unlinked. So this is an example of a virtual slice knot, and it's a non-trivial virtual knot that's sliced. One would like to classify virtual knots up to concordance. One can define a concordance group just like you do in classical knot theory, and there are lots of unsolved problems there. Now, what about Corvanophomology for virtual knots? We're going through this little survey. Well, the problem with Corvanophomology for virtual knots is that there's an extra structure. When you can sometimes re-smooth, and you end up with a single circle. So one way to solve this problem is to call that map 0. And there are other approaches due to Tupinauer and Rushworth that you can look at, but we're following equal to 0. And then there's a good solution due to Monturov, which first observes that a problem diagram like this one, you see this is single cycle, that would be 0 going around the top. But if you go down and to the right, you get a composition of a multiplication and a co-multiplication, get multiplication of x by 2, but multiplication by 2. So mod 2, it works fine. And if you wanted it to work over the integers, you'd have to flip a sign somehow. Now I'm going to make a long story short by even skipping the next result, the next example, because we're edging on time here. The method by which we do this, a little bit different from for Vasily's method, is that we put a source sink orientation at every crossing. And then when it's a virtual knot, that causes some cut points to happen. You see, if you put a source sink orientation everywhere, then from the cut point, it's going directly into that crossing, but you have to go in the opposite direction in order to fulfill the orientation at a nearby crossing. So the cut points are places where you would have to reverse the orientation in this. And what we're going to then do is we're going to use the cut points to do a count. And the count has to do within the algebra. When you're doing the algebra, you have the algebra localized. It's a local coefficient system. The algebra is localized at a crossing in order to do one of our multiplications or co-multiplications. And then you may have to move the algebra to another site. And you count how many times you go through the cut points. And if you go through a cut point, you change x to minus x and you leave 1 alone. It's an involution on the algebra. And then that causes the signs to switch correctly with some extra technology there as well that I haven't mentioned, and gives you a method to do using local coefficients, Corvanophomology for virtual knots. Now, the key thing is that you have this cut locus involution, and you apply it also in the case of the Lie algebra. And in the Lie algebra, the involution is to switch red and green. And when you use the rule of switching red and green, you can then label your diagram with red and green, and you get the correct, I'll give you another example, you get the correct labeling for red and green to create the cycles just like you did in the classical case, so that the Lie cycles reappear with the cut point conventions in the virtual knot theory. And that means that one can repeat the construction of the Rasmussen invariant essentially verbatim and get the same theorems about positive knots and links by using the Lie algebra in relation to the Corvanov algebra, and the structure goes through. So we end up with this theorem that a positive virtual knot has virtual four-ball genus equal to the genus of its Seifert surface, and that means that the reconnection number for a positive virtual link is given by our same formula as before. So here's a picture of an example of a positive link, and the cut points and the way the G's and the R's work. By the time it's labeled, you get G's and R's between different components that are G's and R's different. So that when you multiply it, it comes out 0, and this represents a cycle. So it's that same story. And it's interesting that that the thing does go over. And so then we can play the same game that we did before of reconnecting everybody but one. Here's 2 Seifert circles, and I chain them by leaving them alone at one point and reconnecting elsewhere. And that's the story of how this vortex reconnection problem does reach all the way over to virtual knot theory to get a result about reconnection numbers for virtual knots. But I would not know what it would mean yet to have a virtual knotted vortex. It would, of course, mean that we would have to think about knotted vortices in 3 manifolds. So I think that this talk ends with an interesting question without any mathematics associated with it yet, which is, how can we study knotted vortices in 3 manifolds, and could we even study them in some experimental way as well as a mathematical way? And what will it tell us about 3 manifolds? What will it tell us about the vortices? So that's my story, and I thank you for listening. Oh, yeah, I think I'd best call that my story and stop the talk at this point, because our time is up. I could say more about experiments with vortices and other things. We'll stop here. Oh, I'm sorry. I meant to give you a conclusion slide. Sorry. It's nice to have a conclusion slide. Here's a conclusion slide. Okay. Oh, I don't know why that flipped. Never you mind. Thank you very much for listening.
And I suppose we have time for just one question. So please.
Yes, I
Please use a mic here. Very short, please.
As I understood, you reclaim the Chicago experiment with vortices, and you are interested about the complexity of configuration, and genus is very nice because the number of reconnection is very nice related with genus. And my question is, if you take a real experiment, as I know, you have very often right-handed vortex ring, because it's very natural to do such experiment with right-handed. If there is some special kind of calculation, simplification in Corvanophomology relates with right-handed links, or it is just non-important.
I'm not sure what your question was exactly. You want to know about other kinds of links?
In experiment, you usually take right-handed vortices.
Right-handed? What do you mean by a right-handed vortex?
In theorem, we have genus relate with Birkhoff section in left-handed models. In your theory,
oh, you mean the sense of rotation in space around the vortex line?
And on this rotation, you have some fluctuation which comes from genus complexity of configuration. Are there some...
Yeah, right. That's certainly true. I don't know what it would be like to have a right-handed vortex interacting with a left-handed vortex. If you could have them produced separately, perhaps in some way, and then they would come together. But I wasn't thinking about what would happen there. That's interesting.
Mm-hmm. Thank you very much.
Thank you very much. Okay, thank you very much for beautiful talk. You have a very schedule. Thank you again.